So this is a little article that came out in Science News in 2025, just after the Nobel Prize in Chemistry was handed out to people who invented the metal organic frameworks. This is kind of an interview plus a summary of their findings, and I am interested in this because before they won the Nobel Prize, I had covered this topic a little bit before, because they are used for capturing carbon dioxide from the air in a flow-through system, and they are used for producing water out of the air by capturing humidity even in the driest of places. So seems to have potential solutions for carbon capture and sequestration and sustainability, water, etc. So let's just read this general knowledge I'm learning along with you. The winners of this Nobel Prize in 2025 were Susumu Kitagawa of Kyoto University, Richard Robson of the University of Melbourne, Australia, and Omar Yagi, University of California, Berkeley. So this year's Nobel Memorial Prize in Economic Sciences honors 3 researchers who have shown how innovation drives economic growth. This we covered elsewhere in terms of how they argued that science, investing in science, research, etc., actually can help economic growth, and I converted growth into development based on Herman Daly's work, because growth in general is not as holistic as development, and just in terms of exploiting economic resources and so on. So I will skip that part. I included it here just in case you want to know. The same issue also had this, and there are a few questions and answers from the reporters to these economic Nobel laureates. Talks about lab works on artificial intelligence. How does the creative destruction tie into this? Because the economic work or the work that won the Economics Nobel Prize said that there is something called creative destruction. So things that come along and disrupt the employment situations, markets, etc., are not always bad. That somebody may pay a price in terms of losing jobs, but in the end they allow for economic growth and development. So the creative destruction is essential for growth. And how can creative destruction help develop technology for fighting climate change? We can read that part. Incumbent firms that innovated a lot in dirty technologies tend to continue spontaneously innovating in dirty technologies while pressuring governments to prevent the entry of new firms and pro-green policies to protect their own interests. New firms are not wedded to past bad habits though, so creative destruction tends to push for green. If you allow for more creative destruction, you are helping green innovation. Is that wishful thinking, or is that real? Right now, we have talked about how green preferences by consumers can actually lead to greenwashing by corporations unless there is very solid monitoring and transparency in what they mean by green technologies, etc. And the other question is on science policies in the US, which obviously has political overtones, so let's leave it there. Let's come to architects of molecular cages in winning the chemistry Nobel. Sponge-like materials called metal organic frameworks can separate and store gases. That's the tagline of the article that appeared in Science. As early as the 18th century, people knew the pigment Prussian blue. I should stress the right part. As early as the 18th century, people knew the pigment Prussian blue had the mysterious ability to absorb and hold water. Its structure, deciphered much later, showed the compound was in fact a molecular cage, a cubic arrangement of ions joined by nitrile groups, so carbon and nitrogen linked by a triple bond, we'll see in a minute. This year's Nobel Prize in Chemistry has gone to 3 researchers who pioneered modern versions of these porous structures by using organic molecules as struts to link up metal atoms. The Nobel-winning work by Susumu Kitagawa of Kyoto University, Richard Robson of the University of Melbourne, and Omar Yagi of the University of California, Berkeley, as we mentioned before, led to metal organic framework, or MOFs as they are referred to, with large voids tailored to trap specific molecules, making them useful for storing gases such as hydrogen and methane, or soaking up water vapor or carbon dioxide out of the air. Some believe they even have the potential to deliver drugs or catalyze reactions. I'm delighted with this news, says Andrew Goodwin, a material chemist at the University of Oxford. A lot of people have been waiting for it. It really developed a new field of chemistry. And it's very clearly having a major international impact. The initial breakthrough came from Robson in the 1980s. He created a tetrahedral molecule using nitrile groups to link up copper ions at each of the 4 vertices. Moreover, he was able to stack these molecules into a repeating crystalline structure with large cavities. It was just amazing imagination that he had to devise. It was just amazing imagination that he had to devise in fairly simple terms this way of making a new class of materials. Okay, here is a couple of grams of the new material MOF5. Have the surface area of a football field. A couple of grams of this material can be spread over the surface area of a football field in the US. That's like, I don't know, is it 30 yards by 100 yards? It's fairly, or if it's a soccer field, then you can figure out how large it is. It's not tiny, right? So Robson's material was quite fragile and prone to collapse, but Kitagawa saw the potential. In the 1990s, despite meager funding, he had a thin 2D structure that could hold acetone molecules in its cavities. In 1997, he and his team succeeded in making 3D crystal with cobalt, nickel, and zinc ions as the hubs, so metal organic. You can see where the name comes from. It was threaded with open channels, enabling it to absorb and release methane, nitrogen, and oxygen. It was stable. At first, everyone thought such structures would fall apart immediately. That was common sense. That's why they said it may fall apart. Kitagawa said last week this at a press conference organized by Kyoto University, but we proved that stable, robust frameworks could in fact be built this way. In 1999, Yagi, then at the University of Illinois Urbana-Champaign, revealed the work that would cement the status of metal organic frameworks. Instead of linking up ions, Yagi and his team used more complex metal clusters as the hubs. So you can see what we have vertices and links and hubs that we are talking about. Their iconic material, known as MOF5 or MOF5, was a cubic lattice with huge cavities. A couple of grams of the material have the surface area of a football field. The researchers also showed they could tailor the voids and their properties. So you can then make it specific for capturing CO2, methane, water, etc. By using longer or shorter organic linkers and exposing metal ions in the pore spaces, they could tune the materials to attract specific gases at mild pressures and release them as the pressure drops. So idea is not just to trap them, but if you trap CO2 from the atmosphere or methane or water, you will have to release it to use it. So you need adsorption, desorption kind of approach. It's not called adsorption here. You're trapping and releasing. So I don't know what the appropriate chemistry word is. Let's see if they provide it. When I read it, I didn't see it. Okay. So the number of design possibilities is immense, Yagi said last week at a press conference organized by UC Berkeley. If you think it, you can make it. Today, researchers have conjured up tens of thousands of kinds of metal organic frameworks, and dozens of companies are trying to commercialize their use. They have huge importance for humanity, says Wendy Lee Queen, an inorganic chemist at the Swiss Federal Institute of Technology in Lausanne. Some companies are trying to use them to store methane fuels for cars, whereas others see potential for trapping hydrogen, a clean fuel that otherwise requires high pressures, cold temperatures, or large volumes of store. If you have a couple of grams that can be stretched over such a large area and it can hold hydrogen, you obviously have solved the storing problem at least. Another application is to use the selectivity of the materials as a filter to soak up particular compounds. Yagi's group has spun off companies developing metal organic frameworks to pull pure water out of thin air, even in desert environments. Other companies are testing the materials to extract carbon dioxide from industrial processes and power plants to reduce greenhouse gas emissions. The materials could also be used to sequester toxic wastes or simply to identify when they are present. Presence absent tests can work very well with MOFs. Jing Li, an inorganic and materials chemist at Rutgers University, has experimented with using metal organic frameworks to detect explosives and toxic vapors. Now she's developing some that can separate mixes of hydrocarbons into various petrochemical products. Metal organic frameworks could be more efficient than traditional approaches such as distillation, she says. There has been tremendous progress, according to her. In theory, metal organic frameworks could even be used as catalysts. Reagents could be implanted in the cavities, and reactions could progress through different steps as compounds pass through the corridors of the material. At the Kyoto press conference, Kitagawa said his dream was to use the materials not just to separate and capture the components of air, i.e. nitrogen, oxygen, water vapor, and carbon dioxide, but to convert them into useful products. From these simple elements, CHONN, we can make proteins, food, and fuels. He said air in that sense is invisible gold. We are breathing in and out and polluting it, and it's just sitting there. And if we can do this cheaply, obviously we have found real invisible gold. And then how we will fight for it is not so obvious. But anyway, I'm not adding much information to the basic text provided, but it's useful. I found it useful to read, so I'm reading it to you. Hopefully you can follow up if you are interested in more details. Okay, see you.